Hello. So you guys are doing okay. Let me give you guys the usual things. Here's the links to the attendance and the tutoring. Please do them when you have a chance. I'm sure I'll post them like 5 more times. Do that in the chat. I feel like, so actually let me ask. Leslie, you just joined. I assume you can't see what I typed in the chat, right? Is that true, Leslie? Leslie, I'm asking you a question. I assume that's true. All right, so what do you guys have questions about? I've got lots of things I'm sure we can talk about, but are there any homework questions that we still need to go over? Or any concepts from the homework questions? Okay, that's what I thought. Thanks, Allison. I appreciate that. That's what I assumed. I feel like that's something that could be the thing. I don't know. I would like to imagine that's something that could change, but who knows? All right, there's the attendance and tutoring again. So, what do you guys want to talk about? Or have questions about? Yeah, we can definitely go over L'Hopital's rule. Yeah, so L'Hopital's rule, we'll definitely talk about. What I want to say about it first off is, though, is that it probably doesn't come up a whole lot in this class, like compared to other calculus classes. It probably gets used minimally. That said, it is still something we have to be able to use. And I imagine he's going to ask you about all the ways, so I want that to look. So yeah, let's talk about L'Hopital's rule. Oh, also, I wanted to mention, I just posted for you guys, I think like 4 or 5 videos, one on global maxes and mins, one on the inverse function theorem, one on Taylor polynomials and linearization, and then a couple on related rates. They're not linked in Canvas yet, but they are on the YouTube page, and you can find them under the 17A short videos or 17A week 8 videos. But I will also link them in Canvas after class. So those are there if you need some examples of those things. This board seems like it's getting squeakier every day. Okay. So, L'Hopital's rule. So the important thing to remember about L'Hopital's rule is the only time you're allowed to use L'Hopital's rule is taking a limit, and it has to be a 0 over 0 or an infinity over infinity type. Those are the only times we're allowed to use it. So for L'Hopital's rule, and some people say it differently, they're wrong. That's how you're supposed to say L'Hopital, it's French. You have to say La Hospital, drives you crazy. But so L'Hopital's rule says if you have the limit, as x goes to something of f of x over g of x, and you either have it's equal to the limit as x goes to a of f prime of x over g prime of x, sorry, g prime of x. So basically, you take the derivative of the top and the derivative of the bottom. And this is perfectly fine if it's a 0 over 0 or infinity over infinity type. And when I say infinity over infinity, I mean any type of infinity. So it can actually, these don't have to be the same. It can be a positive infinity over positive infinity, or a positive infinity over negative infinity, or a negative infinity over positive infinity, or a negative infinity over negative infinity. Any type of infinity over any type of infinity, you're perfectly allowed to use L'Hopital's rule. So let's look at a few examples that we already know the answers to. For example, the limit as x goes to infinity of 2x squared plus 3x plus 7 over 5x squared minus 2x plus 1. This is definitely infinity over infinity type. The top's going to infinity, right? We've got 2 times infinity squared plus 3 times infinity plus 7. That's going to infinity. The bottom is also going to infinity, although we should say more about it. I've got 5 times infinity squared minus 2 times infinity, but this is a much bigger number than that one. So this one overrides this. And really for rational functions or polynomials, we only pay attention to the biggest term. So these are really the terms that matter. This is going to infinity, this is going to infinity. So the bottom's also going to infinity. So then we can use L'Hopital's rule because it's an infinity over infinity type. So you can see that this limit is equal to the limit as x goes to infinity of the derivative of the top, which is 4x plus 3 over the derivative of the bottom, which is 10x minus 2. It's still, oh, I should have started, sorry. Before I got going down this whole path, I should have asked you guys, what is the limit of this, right? You know from previous experience, the limit of 2x squared plus 3x plus 7 over 5x squared minus 2x plus 1 as x goes to infinity should be what fraction? Yeah, exactly. Definitely 2/5, right? We know that because you can either divide it from x squared, or you can just say, right, we know that the degrees are the same, so the limit is just the quotient of the leading coefficients. But you can also use L'Hopital's rule to get there. So here we still have an infinity over infinity type because the top is going to be infinity and the bottom is. So then we can use L'Hopital's rule one more time. Oh, and I'm going to say something about this in a second. The derivative of the top is 4. The derivative of the bottom is 10. Now I want to be super important. Clear here. We don't need to, but we couldn't use L'Hopital's rule again even if we wanted to, right? Because now it's not a 0 over 0 or infinity over infinity type. It's just a constant. And the limit of a constant is just the constant. So my answer here is going to be 4 over 10, which reduces to 2 over 5. So there's an example of one we already knew working with L'Hopital's rule. Also, just as an aside here, when I use L'Hopital's rule, I typically write above the equal sign. This is pretty, it's not required. Oh man, all this black dust, so terrible. Sorry. It's not required, but it's pretty standard to write L'(H) in the stuff that you use in L'Hopital's rule. So from here to here, I use L'Hopital's rule to get this next expression. And then from here to here, I use L'Hopital's rule to get that. From here to here, I didn't, so I'm not going to write it over there. But every step where you're using L'Hopital's rule, where you're writing the limit and taking the derivative of the top and the derivative of the bottom, it's good to write that so the person reading your work knows what you're doing. Something else I want to say here. There really was something else I want to say, I thought. Oh, I know what it was. Another thing to be careful about is you're not using the quotient rule, right? This is definitely not the quotient rule. We're not even taking the derivative of this function, right? We're just using the derivative as a tool to help us evaluate this limit. So I want to make it extra super clear. You only get to use L'Hopital's rule, first of all, when you have a limit, right? It's not good for derivatives or anything like that. You use the derivative for it, but we don't use it to take a derivative. So you only get to use the L'Hopital when you have a limit, and it has to be one of these two types. There are other types that we can modify or manipulate to be able to use L'Hopital's rule, but you cannot use L'Hopital's rule unless you have a fraction. And the fraction has to be this or this, or like both of those. So let's look at a couple more examples that we already know. So for me, sometimes the hard part is knowing, God, this board, when to use L'Hopital's rule. There's also, yeah, I've got some good examples. Okay. So here's another example that I think shouldn't be too terrible. The limit as x approaches, let's go 3 of, what do I want here really? I want, sure, x squared minus x minus 6 over, x squared minus 9. Clearly, well, maybe not. Let's plug it in and make sure. If I plug in 3, I get 9 minus 3 minus 6, which is 0 over 9 minus 9. This is definitely a 0 over 0 type. We could do it without L'Hopital's rule. But let's go ahead and do it without L'Hopital's rule. Without L'Hopital's rule, right, the way I would normally attack a function like or a limit like this is by factoring the bottom factors as x minus 3 times x plus 3. The numerator factors is x minus 3 times x plus 2. We cancel the x minus 3's. We have the limit as x goes to 3 of x plus 2 over x plus 3. So we just plug in 3, and we get 3 plus 2 over 3 plus 3, which is 5 over 6. However, we can also use L'Hopital's rule. Instead, you can say, well, this is going to be using L'Hopital's rule. The limit as x goes to 3. The derivative of the top is 2x minus 1. The derivative of the bottom is 2x. I can't use L'Hopital's rule again because I no longer have it. So basically, every step after you use L'Hopital's rule, you kind of ask yourself, can I plug in the thing? And if you can, you just stop there. So can I plug in 3? Yeah, I get, well, can I plug in 3 and not get undefined? So I plug in 3, I get 6 minus 1 is 5 over 6. Same answer. So you might be asking, well, why L'Hopital's rule? Because sure, I could have done these limits another way. Well, the thing is, there are some limits that you can't do without L'Hopital's rule. Let's do, actually, before we get there, though, let's do one more that we can. One that you guys know really well, or at least I think you know really well. The limit as x goes to 0 of sine of x over x. Well, we know that's 1, right? We did it like a bunch of times. But now you can use L'Hopital's rule and say, well, that's the limit as x goes to 0 of cosine of x over 1, right? Derivative of sine is cosine, derivative of x is 1. And then plug in 0, I get cosine of 0 over 1. Cosine of 0 is 1. So I get 1. This is another way to find the limit of sine as x goes to 0 sine x over x. And it even kind of helps explain why those other limits, I mean, not that we didn't see how they were before, but it kind of explains how, or is another way of seeing how those other limits work. Like, for example, the limit as x goes to 0 of sine of 4x over 3x. We could use the wish method and end up getting 4/3, right? Because you like, so one way to do this would be say, oh, it's the limit as x goes to 0 of sine of 4x over 4, well, over something times something over 3x. And then we put a 4x down here and a 4x up there. And then this would go to 1, the x's would cancel, and you get 4/3. But then now we kind of bypass all that and just say, well, instead of doing that, I'm going to take the derivative. I'm going to use L'Hopital's rule and take the derivative of the top and the derivative of the bottom. The derivative of 3x is just 3. The derivative of sine of 4x is cosine of 4x times the derivative of 4x, which is 4. Right? So change it to get cosine of 4x times 4. Now I plug in 0. Cosine of 0 is 1, and I get 1 times 4 over 3. So it definitely works. There are some examples, so let me do one more example of one we know, where you actually don't want to use L'Hopital's rule. So most of the time, L'Hopital's rule is great. Sometimes it's a tool that's just, it doesn't work as nice as something else. So here is another example. And I think we did something like this. So let me, I'm pretty sure. So like the limit as x goes to 0, sine squared of 2x over 3x squared. We can use L'Hopital's rule here. And for this one, it's not too terrible, but it's pretty terrible. So let me show you. So this is sine squared of 2x is really sine of 2x quantity squared. So I was going to use L'Hopital's rule. Well, so actually first, I'm getting ahead of myself. I should first verify, can I use L'Hopital's rule? Is the denominator going to 0? Yes. Is the numerator going to 0? Also yes, because sine is 0 is 0. So you should always be asking yourself before you use L'Hopital's rule, is it 0 over 0? Is it infinity over infinity? The answer is yes, go ahead. If the answer isn't, you gotta do something else. So now I'm going to take the derivative of the top and the derivative of the bottom. The bottom is 6x. The derivative of the top, so let's say I've got some stuff squared, so I have to use the chain rule. It's 2 times my stuff times the derivative of my stuff. And the derivative sine of 2x is cosine of 2x times 2. And we can probably cancel the 2. I don't think it's really important. Might as well sure cancel this 2, cancel that 2. So now I've got the limit as x goes to 0. I don't even really care about, right? This 2/3, let's write out in front. But then I've got a sine of 2x times a cosine of 2x all over 3x, which is still a 0 over 0 type of limit. Sine of 0 is 0, cosine of 0 is 1, top is 0, the bottom is also 0. So I can use L'Hopital's rule again. And this is where things are going to get a little bit beastly. So I've got the limit of this term's life as x goes to 0 of 2/3 times. All right, so on the top I have to use the product rule. So I'm going to get the derivative sine of 2x, which is cosine of 2x times 2 times cosine of 2x plus now sine of 2x times the derivative of cosine of 2x, which is negative sine of 2x times 2. Look. All over 3. I definitely know at this point I can't use L'Hopital's rule again because the denominator isn't going to be a 0. So I just plug in 0, and here's what I get. I get 2/3 times cosine of 0 is 1, so 1 times 2 times 1 plus sine of 0 is 0, so 0 times whatever is 0. All over 3. So I end up with 2/3 times 2/3, which is 4 over 9, which I feel like could actually be wrong. Did I make a dumb error? I totally made a dumb error. Do you guys see it? It's kind of hard to see, I'm not gonna lie. I factored out the 2/3, but then I still wrote the 3 down there. So there shouldn't be a 3 there. 4/3. And this is all fine, but what I want to point out is for this problem in particular, it's probably easier just to use the wish method that we already developed. Right? I could totally instead say, well, the limit is sine of 2x as x goes to 0, sine of 2x squared over 3x squared. I can write that as the limit as x goes to 0 of sine of 2x over blank times sine of 2x over blank times blank over 3x squared. And then I wish I had a 2x here, which means I need one here. I wish I had the 2x here, which means I need one here. These both go to 1, and then the x's cancel, and you get 2 times 2 over 3, which is 4/3. So in these particular kinds of ones where you have a sine to a power over x to that same power, usually the wish method is a little bit easier than L'Hopital's rule. Especially like if this was sine cubed, it's really, like I've done the cubed one before, it's really terrible. So then you're basically taking the derivative of something like this again, and it's just like super messy. So sometimes, even though you can use L'Hopital's rule, it's a real giant pain to do so. All right, so what kinds of things can we use L'Hopital's rule for? Or I should say, what kinds of things do you need to use L'Hopital's rule for? Oh, there's definitely one that's been coming up in my 17B and 7. Well, I'm not doing 17B, but it definitely does come up in 17B and 17C. So, how do I want to phrase this? Yeah, sure. Let's look at this. Yeah. The limit as x goes to infinity of, say, like x cubed over e to the x. So this is definitely infinity over infinity type. X is going to infinity, so is e, so x cubed is, so is e to the x. So here I use L'Hopital's rule, and you get the limit as x goes to infinity of 3x squared over e to the x. Right? The derivative of x cubed is 3x squared, the derivative of x e to the x. Now, you can kind of start to see what's going to happen. For a polynomial, you're going to keep taking the derivative each step and getting a 1 less power of x until you get down to like a constant. For the e to the x, the derivative of the x is always just going to be e to the x. So every step you're going to get, in this case, the top being closer to a constant and the denominator just staying the same. Right? The derivative of the x for the 6x, the derivative of e to the x and e to the x. And then the derivative of 6x is 6, the derivative of e to the x is e to the x. So now I got 6 over something that's infinitely large, that's going to be 0. And so what we see here is that this would be true if it was x to the third or x to the 100th. And so what you can kind of learn from this is that an exponential function like e to the x is always eventually going to be larger than any polynomial function. So as x goes to infinity, e to the x is going to always be bigger than x to some positive power p, no matter what the power is. It can be x to the millionth power, right? So, and this one's going to start off slow, right? If x was 2, e squared is definitely smaller than 2 to the millionth power. 2 to the millionth power is super freaking big. But eventually, as you let x get larger and larger and larger, e to the x is going to overtake x to the whatever millionth power you have. It's kind of neat. And that's true for any exponential function where the base is larger than 1. Even if the base was like 1.1, eventually 1.1 to the x is going to be larger than x to the million. It takes a long time, but it does happen. All right. Let me see. Let me have you guys try one here. Why don't you try this? How about the limit as x goes to 0 of, let me make sure I do this right, sine of x minus x over x e to the x. Sorry, just 1 sec. Let me take 1 sec. Plus x minus x. So let me think. Let me make sure this is what I want. Yeah, that's right. Okay, go ahead and try that one. And I'll give you a minute to a minute and a half. I'm gonna give you a restroom break, and I need to give me a restroom break. So work on that one. It should take 2 iterations of L'Hopital's rule. Okay, I think it's been about 90 seconds-ish. So I see, first of all, it is a 0 over 0 type. Sine of 0 is 0, minus 0 is 0. 0 times e to the 0 is 0, minus 0 is still 0. So then I use L'Hopital's rule. Still have to write the limit, because I'm still taking a limit. Derivative of sine of x is cosine of x. Derivative of x is 1. Derivative of x e to the x, I have to use the product rule, so I have to be a little bit careful here. Derivative of x is 1 times leave e to the x alone, plus leave x alone, times the derivative of e to the x is e to the x, minus the derivative of x is 1. Now if I plug in 0, I think I still get a 0 over 0 type, but let's double check. Cosine of 0 is 1, 1 minus 1 is 0. And I plug in 0 here, e to the 0 is 1. 0 times e to the 0 is 0 minus 1. So it gets 1 plus 0 minus 1, which is still a 0 over 0 type. So then we do it again. Or usually if you get right, you just keep doing limit as x goes to 0. Derivative cosine of x is negative sine of x. I want this one to turn off to 0. Oh, well, fine. Sometimes life happens. The derivative of the bottom at minus 1. Derivative of 1 is 0. Derivative of the bottom, so derivative e to the x is e to the x. The derivative of x e to the x, we actually just did it, right? The derivative of this was this. So the derivative of x e to the x is e to the x plus x e to the x. And then the derivative of 1 is 0. So I end up getting, let's see, sine of 0 is 0 over 1 plus 1 plus 0. So I get 0 over 2, which is just 0. Which always feels not very exciting, but that's what we get. So I should ask you all. No, I shouldn't do some. So sometimes you have to work before you can actually use L'Hopital's rule. And the next couple examples are the ones that I think come up the most in your future classes. Definitely, I've been talking about this limit in my classes. So I would say that the limit as x goes to infinity of x squared times e to the negative x, which is definitely not written as a fraction. This is actually another type of indeterminate form. So x squared is going to infinity. E to the negative x as x goes to infinity is going to 0. If you think about the graph, e to the negative x looks like this. By the way, I should post up just in case anyone didn't get it yet. Here's the attendance form again. Please do fill it out. Sorry. So e to the negative x is like this, and as x goes to infinity, e to the negative x is going to 0. So this is what's called an infinity times 0 indeterminate form. And the thing that's important to recognize here, to know, is that infinity times 0 can be anything. It doesn't have to be 0. Because, again, it's not really infinity times 0. It's a big number times a small number that isn't actually necessarily 0, right? E to the negative x doesn't actually ever equal 0. It's just getting smaller and smaller and smaller. So when you have a big number times a small number, it's unclear which one's winning, is how I kind of think, right? Is the big number big enough that it's overpowering the small number, making this thing really big? Or is the small number small enough that it's overpowering the big number, making it really small? Or is there some like in-between place where they're kind of balancing? Anything can really happen. So in this case, the job we have is always to rewrite it as as a fraction. So you can either write it, and here's where we have to make a choice. You can write it as the limit as x goes to infinity of x squared over 1 over e to the negative x, or the limit as x goes to infinity of e to the negative x over 1 over x squared. And the thing you kind of want to keep in mind is you want to kind of pick the one that's going to be easier to differentiate the bottom and get somewhere. And so you can kind of agree that you can kind of say either of these are, but if you think about this, 1 over e to the negative x is just e to the x. And 1 over x squared is just x to the negative 2. And so depending on how you write it, you either have a 0, 0, 0 over 0 or an infinity over infinity. This is infinity over infinity, right? You've got x going to infinity, so x squared is e to the infinity. This is a 0 over 0. E to the negative infinity is going to 0. And x to the negative second, which is 1 over x squared, is also going to 0. So let me show you what happens. So if we do this first one, things work out nicely. The limit as x goes to infinity, so I'm using L'Hopital's rule. Derivative of the top is 2x, derivative of e to the x, d to the x. Do it again. Right, this is just like one we did before. Derivative of 2x is 2, derivative of e to the x, d to the x. 2 over something that's really, really big is going to 0. So here the 0 wins out. If we try to do it this way, things are not going to work out nicely. You're going to get the limit as x goes to infinity The derivative of e to the negative x is e to the negative x times negative 1. The derivative of x to the negative second is negative 2 times x to the negative third. The problem is this is still a 0 over 0 type. E to the negative infinity is still going to 0. 2 times x to the negative third, or 2 over x to the third, is still going to 0 as well. And the problem is this thing got further away from being nice. And the power was x to the negative second, now the power is x to the negative third. If we do another derivative, the power is going to be x to the negative fourth. If you keep going down this road, you're not going to get anywhere. It's going to just be worse and worse and worse. So usually there's one way that works just fine and one way that doesn't work at all. And here's this one. So now I should stop and ask you guys, did he talk about ones like this, where you have an infinity times a 0? Okay. This is probably the prime example of the kinds of things you might see in the future where you have to evaluate a limit like this. So I don't want to stray too much into this because, well, it's not super important unless you have to know it. Let me do like 1 or 2 more examples, and then you guys should be thinking of what else you would like to ask me about. I'm certainly happy. I can talk about L'Hopital's rule all day, but if you want to see other things, you should say so. So another example of this would be something like the limit as x approaches 0 from the right of x cubed times the natural log of x. And here's the attendance once again. We're looking at some L'Hopital's rule stuff. Please feel free to ask me other things you want to say. So I just want to point out, this is also a 0 times infinity type. And now, I should be really, really explicit, right? X cubed is definitely going to 0. 0 cubed is 0. Natural log of x is going to negative infinity, right? If you think about the graph of the natural log of x, which looks like this, as x goes to 0 from the right, the natural log function goes down to negative infinity. So this is definitely a indeterminate form. And so again, we want to bring down the thing to the denominator that's going to be easy to take the derivative of. Now, so we have, I'm just going to present the choices. You could either do this, x cubed over 1 over natural log of x. That does not look like it's going to be particularly nice to differentiate. I would actually need to use the quotient rule there, or write it as natural log of x quantity to the negative first and use the chain rule. Or I could write it as the limit as x goes to 0 from the right of the natural log of x over 1 over x cubed. And this is a lot better because 1 over x cubed is easy to simplify, right? Or it can be rewritten as x to the negative third, which is easy to differentiate. So in this case, in fact, I will say this case is kind of the exception, where the e to the x is the thing that's on the bottom. Most other cases, if you have an x to a power, that is usually the thing that ends up on the bottom. So let's see. Doing it this way, I'm going to write this as the limit as x goes to 0 from the right of natural log of x over x to the negative third. And then we're going to differentiate both the top and the bottom, right? So we're going to use, I really should say, we're going to use L'Hopital's rule, which means we have to differentiate the top and the bottom. We have the limit as x goes to 0 from the right. The derivative of the natural log of x is 1 over x. The derivative of x to the negative third is negative 3 x to the negative fourth. And now here's where you have to be kind of savvy. Right? I'm going to rewrite this as the limit as x goes to 0 from the right of 1 over x over negative 3 over x to the fourth. And if we were kind of stuck in the mindset of L'Hopital's rule, we might make the mistake of doing it again. Not that it's necessarily wrong, it's just not the way we want to go. It definitely is the right form though, right? 1 over 0 is going to positive infinity since x is going to 0 from the right. Negative 3 over 0 to the fourth is going to negative infinity. So this is an infinity over negative infinity type. But I don't want to use L'Hopital's rule if I don't have to. What I want to do is I want to simplify this thing. Right? This definitely simplifies. I can write it as the limit as x goes to 0 from the right of 1 over x times the reciprocal of negative 3 over x to the fourth. which is x to the fourth over -3. And x cancels here, and x cancels here. So I really got the limit as x goes to 0 from the right of x cubed over -3, and then plug in 0, and you get 0 over -3, which is 0. So sometimes after you use L'Hopital's rule, you don't want to use L'Hopital's rule again if you can simplify things first. Okay, I think I've said a lot about L'Hopital's rule, but so are there other questions about L'Hopital's rule, or are there specific examples you might like to see? Is there anything else you guys have questions about? I think Sanders people have a quiz sometime. I couldn't see what it was because I don't know how to access it, or if I'm able to access it. Sorry, 1 second. Okay. Okay, are there other questions that are not about L'Hopital's rule? All right, well, let's talk about related rates, since that's something people definitely have added for. So there are a couple of examples on YouTube, and I'll post the links up to on Canvas right after class. But here's an example that I've seen in the past that definitely comes up. So here is the setup. A 6 foot tall person. Person? No. Try spelling person the right way. Person walks away from a 20 foot tall street lamp at a pace of 5 feet per second. So I'm going to phrase this the way I usually phrase it, but then I'll talk about how some books phrase it. How fast is the length of the shadow of the person changing? Okay, so of course, I'm going to draw a picture. So here's my picture. I've got my street lamp here, emitting light. And here's the street. And here's the person who's 6 feet tall. And they're walking away, so they're going that way. And then I'm going to draw the shadow. So this, right, the street lamp is casting this shadow. And then I'm going to start labeling things. So this length here, I usually am calling this, I think, X, I don't know. Right, that length is definitely going to change because when the person is standing over here, right, in fact, we can kind of draw the later, oh, come on, darn pen on the hand. Yeah, not my favorite. Right, so if we think about the person later, right, here's the new shadow that we cast. So then, right, X is getting longer. So X is the length of the shadow measured from the person. It is changing. And what did I want to say? There was something I actually wanted to say. Oh, it is increasing, right? If you're walking away from a light source, your shadow should be getting longer. I should think stationary light source. Your shadow should be getting longer. We also need some other stuff. So I have that the person is walking away from the street light at a pace of 5 feet per second. So something is increasing in 5 feet per second. And it's actually this length here, right? The length, the distance from the street lamp to the person, that's what's changing. So I'm going to call this length, let's call it Y. And here's what I know. I know that dy dt, the rate at which the person is walking, is 5 feet per second. And I'm interested in knowing what dy dt is. Sorry, dx dt is. All right, so we've identified the things that are changing. Now we need to find an equation relating them. And here, I should actually have labeled, I didn't label everything, right? I should have labeled this height. This height's 20 feet. And this guy's height is, or it could be a woman, right? There are plenty of 6 feet tall women. This person is 6 feet tall. So this picture is, I feel like, maybe not quite as useful as if I didn't have all the nice drawing. My drawing is so nice, yeah. So it might be better if I actually just drew it kind of like this, where here's my person that's 6 feet tall, here's my line that's 20 feet tall, here is y, and here is x. So what I actually have is a case of similar triangles. I have this small triangle here, right? I have so here's my big triangle, where the height is 20, and the base is y plus x. And I have this small similar triangle here, where the height is 6 and the base is x. So what I can do is I can say, oh, okay. I'm going to erase my next picture. I can use similar triangles or ratios to say that x is to 6 is the same as x plus y is to 20. Right? If the triangles are similar, the base divided by the height should equal the base divided by the height. So what we can do now is we can use this relation. So we could take the derivative right now, but here we can actually make it simpler. You can cross multiply and say 20x equals 6x plus 6y. And then you can subtract 6 and say 14x equals 6y. And that's pretty much easy to differentiate. So here's our equation relating x and y. Now we're going to take the derivative of both sides. Yeah, I guess I can probably put this in here. So what's the derivative of 14x? It's 14 times the derivative of x, which is dx dt. What's the derivative of 6y? 6 times dy dt. Now I plug in what I know. I know dy dt is 5. So I have dx dt, 14 times dx dt. Equals 6 times 5 feet per second. So divided by 14, 6 and 5 is 30. So dx dt is 30 over 14, which reduces to 15 over 7 feet per second. Now here's the thing that I think is interesting about this problem. We didn't have to plug in y anywhere. Right? It didn't matter that the person was how far they were from the lamp. The rate that their shadow increases in length is wholly dependent on the original setup, right? The heights of the lamp of the person and how fast they are walking. There's no mention of how far they are from the light source in our particular solution. So what we're saying here is that the length of the shadow, if the person is walking at 5 feet per second, the length of the shadow is going to be increasing at 7 feet per second. One other thing about this type of problem, which I've definitely seen come up probably in the 16 series, and this question might come up in your class, but it's definitely something I've seen that I want to make you aware of. So in this situation, sometimes people ask, sometimes normal, reasonable people like myself ask how fast the length of the shadow is increasing, because that seems like the right question. Sometimes other people ask, how fast is the tip of the shadow moving? Meaning you're asking, how fast is this point moving? And when you're asking how fast something is moving, you have to have a reference to something stationary. So what we're really asking is, how fast is this length changing? So if I'm calling still this x and this y, I'm really asking, okay, how fast is ddt? Right, what's the derivative of x plus y? I want to know how fast is the length of the tip of the shadow moving. How fast is this length x plus y increasing? Well, this is super easy if we've done the other part already. Because when you take the derivative of two things added together, it's just the derivative of the first thing plus the derivative of the second thing. And we know both of these from the previous problem. We know that dy dt is 5 feet per second. That's how fast the dude's walking. We know that dx dt, how fast his shadow is moving, is 15.7 feet per second. Sorry, dude or lady. So the answer, and it seems reasonable once I say it, is that if you're asking how fast the length of the shadow is moving, it's just how fast the length of the shadow is increasing, plus how fast the person is walking. And then you can simplify this, right? 5 is 35 over 7, and 35 plus 15 is 50. So you get 50 over 7. So that's how you answer a question like that. What else? Let's see one thing here. So no more midterms left. All right, you guys have your quiz. So we're almost finished week 8 here. Oh, there was something I wanted to say. Where'd you go? No, I guess not. Oh, someone asked, I think I know this. I wasn't sure if it was this class or one class. Someone asked in the discussion about the co-classes for fall quarter. They definitely are available. I will post that up in Canvas so that you guys can see it. It's also just on the AATC website. So if you go to the AATC website and go to the math part, you can find it there. And then there was something else I wanted to say. Oh yeah, there's an end of the quarter survey about this class that I'm going to post in Canvas as well. And I'll probably also email it to you guys. If you could please take it as soon as you can. I mean, it's not urgent that it gets taken right away, but it is urgent. It is important that it gets taken at all. So if all of you could please take that once it's available, I would really appreciate it, as would my boss and the other people that work in the AATC. I think that's about it. I should be grading your quizzes today. And I don't know, you guys have anything? Oh. I know who will be teaching Math 17B fall quarter. I don't know off the top of my head, but we can. And so the truth is, it's probably not known yet. If we look at the math department website, which is where I usually go, especially from like it's usually easier to know from like winter to spring because like they're close to each other. Sorry, the private message. Somebody asked, "Do I know who's going to be teaching 17B in the fall?" And the answer is no, I don't. But if we look at the course list, so I'm looking at the course list on the math department website. So actually, I can share my screen with you guys if you want. But my bet is that they don't know yet either. Is probably the real truth. So if we look here, here's the math department website, math.ucdavis.edu. I'm gonna click on courses and look at the course list. And then I'm gonna go, let's see, fall 2020. And oh, there's actually, so people are listed. Okay, that's, well, so the Dell's listed for 17A. 17B, let's see who we got here. We have Gorski, who I'm not familiar with. And that is the only person, wow, so interesting. So it looks like there's one section of 17B currently scheduled. So it looks like you guys will be having Gorski. That could change in that it is certainly possible that they add another section. It is certainly possible that the teacher changes. I would definitely not say that this is set in stone, but it does seem likely that that will be the teacher. So I would go, I mean, it looks like you don't have much of a choice as to who you get to take, but you might want to go see what you can learn about that person and try and prepare for that. I will also point out that there will be a 17B co-class in the fall. I think I'm scheduled to teach it, but I haven't actually looked because fall feels super far away. But what I will say is that there will be 17B co-class in the fall. There's also obviously summer classes. Now, normally my thought about summer is I don't like to think about doing math in the summer because it feels like it's a real kind of, oh, the website for the co-class, I can give that to you guys. It's just the AATC website. So let me actually grab that here. 1 second. I will also post it, but let me, okay, so that's good. There's a 5 rating. I would obviously take those ratings with a grain of salt. Let's see here. So yeah, so if you go to here, if you go to this link here. You can find if you scroll down to the fall 2020 math pre and co classes, you can find the 17B co class. And let's see, am I teaching it? TBD, we don't know who's teaching it yet. But someone will be teaching it. I'll probably imagine, no, I guess it could be, it's probably me, but maybe we don't know it just because we're trying to figure out who's doing what. There was something else I was trying to say though. Yeah, schedule builder, usually the math department's website usually has it before schedule builder does. But what I will say about the teacher is, I was trying to say, summer is an option. We don't have co-classes during the summer, but all the specialists, myself, Grant, Sarah, Claire, Casey, and Duff, we will be available for online office hours during the summer, kind of like drop-in, where we're going to be seeing more than one person at a time. So that is something that is still there for you if you decide you want to take a summer class. And you might want to take a summer class just because you might not have a lot else going on during the summer. And also, there won't be as much time between now and fall to forget what you have learned. So there are good reasons or arguments for taking a class in the summer, something you might want to consider. The summer classes are not listed, the teachers on the math website, so you would want to go look at the schedule builder to see who is teaching it in the summer. All right, that's all I got. We're out of time. So I will try and post those things up on Canvas. I'll also post the links to the videos I posted if you want to go look at those. And let me know, as usual, if you guys have questions, feel free to let me know. Take care. I'll see you guys on Friday.